Once we have defined an electron configuration for an atom, there can be several terms associated with that particular electron configuration. As an example, we've seen that carbon, and I've miswritten this a little bit up here, carbon, which has an electron configuration of 1s2, 2s2, 2p2, has 5 different term symbols that correspond to that particular configuration. Well, what's the difference between those? Well, it turns out that each of these different terms have different state energies. They may not vary by a lot, but they are actually detectable experimentally. So they have different energies associated with them, and this happens because there is electron-electron repulsion among those various electrons in the different orbitals. So with these different state energies, a logical question to ask then is which one is the lowest? Which one would be the ground state for the carbon atom, or for any atom, for that matter, once we've found its term symbols? Well, in order to determine this, we use something known as Hund's rules. These are rules that were put together empirically by a physicist named Hund. And it basically goes as follows. We're going to set up different priorities for how we determine the lowest term. Now, I want to be careful to state right up front, this is a great way to find the lowest energy term, but it does not necessarily tell you the order of the other terms. That is to say, you can find the lowest energy one using Hund's rules, but you cannot necessarily put them all in energy order using these rules. Okay, so first priority is that this term with greatest multiplicity, greatest spin multiplicity, would be the ground state. All right, so spin multiplicity is the 2s plus 1 is the multiplicity. All right, the second priority would be if if you have more than one term with the state with the same multiplicity, then states with same multiplicity the one that has the largest value of L. Would be the one that would be the ground state. If somehow you've managed to get this far and you have several different terms that have both the same multiplicity and the same L, then you would look for the state that has an extremum of the total angular momentum value. But that extremum will change depending upon whether your subshell is half full or not. So there's two cases here. One is subshell, in this case for carbon it's the P subshell, is less than half full. In which case we would choose the smallest value of J. Almost got that wrong. Smallest J would be the ground state. If you have a subshell, however, that's more than half full, then it's the largest value of J that would be the lowest energy or the ground state. All right, so we've got these different terms for carbon. Which one is the ground state? Well, from the very first rule, we can eliminate the two singlet terms. So 1s0 and 1d2 are eliminated by the first one. But then we have three different terms, 3p0, 3p1, and 3p2, which all have the same multiplicity and the same L value. Okay, so in this case, what we care about are the J values. We have J equals 0, 1, and 2. Since the shell is half full, it's the one with J equals 0, which is the ground state. Or in other words, the one that will be the ground state for the carbon atom should be the triplet P0. in this case. Now, what you may be given is you may end up being given a series of terms that correspond to a particular configuration and asked to use that series of terms to determine which one is the ground state. So let's do a simple example of that. Okay, let's suppose that the atom we're considering is nitrogen, which is in an electron configuration of 1s2, 2s2, 2p3. Okay, it's one over from carbon. All right, now this would be a good exercise for you to try, but see if you can come up with the terms. You should come up with doublet P, with doublet D, and with quartic S as your three terms. And I'm not going to go through the J's just yet, but we'll see how to get those in just a moment. All right, so these would be your three terms. I hope that it would be pretty easy using Hund's rules to indicate that this one, in fact, would be the ground state for the nitrogen atom. All right, that has the highest spin multiplicity, so you don't even need to know the J values to get that. But just for fun, what would be the J values for these terms? Well, if I have doublet P, all right, what this means is that S must be equal to 1/2. So 2s plus 1 is equal to 2, so 2s is equal to 1, or s is equal to 1/2. Since it's P, that means L is equal to 1, so this means that J can range from L minus S to L plus S. So that means L minus S is 1/2, L plus S is 3/2. So we can get two different terms out of this. We can get doublet P 1/2 and doublet P 3/2. All right, what about the next one? We have doublet D. This corresponds to, again, S equal to 1/2, but now L has got to be equal to 2 for the D label. So this means that J can be equal to L minus 1/2, which is 3/2, or L plus 1/2, which is 5/2. So again, we're going to get two terms that correspond to this. We'll get doublet D 3/2 and doublet D 5/2. All right, finally, for the one that is the winner in this sweepstakes, the quartic S. Okay, in order to get 4 here, that means we must have a spin of 3/2. Okay, since nitrogen has an unfilled shell that has 3 electrons in it, that means that all 3 of those electrons must have the same spin in order to get a spin of 3/2. Okay, L in this case is 0, so L minus S is the same as L plus S when we take the absolute value. So the only value of J that we can get for this is 3/2. And so that means that our single term for this lowest energy term is quartic S 3/2. And this is the ground state for the nitrogen atom. So I hope this helps you navigate through some of these issues when it comes to Hund's rule and the various terms, so that you can identify what the ground state is for any atom that you might find in the periodic table.